Right, good evening everybody. I think it's 5:30, so we can start. Today's lecture will be on extrasolar planets, which are also sometimes called exoplanets for short. And these are planets which orbit stars other than our sun. And I'd just like to preface the lecture with, I am by no means an expert on exoplanets, but I've had great fun preparing this lecture because it's such a fast-moving field. It really, the first exoplanet that we discovered around a main sequence star, and now everybody knows what a main sequence star is, was only in 1995. So this is an incredibly new field of astronomy, and it's literally, it feels as though we're discovering a new planet a day, pretty much. And so it's incredibly exciting, it's fast moving, and there's a huge amount of work still to be done out there, especially with the new upcoming large telescopes that are being built. This picture over here is an artist's impression of some of the so-called hot Jupiter planets which have been discovered by various methods. And what I mean by this is that these are gas giant planets, similar to, if you imagine what Jupiter looks like, and we know what it looks like. We've got many images of Jupiter from various spacecrafts, from telescopes. And these are called hot Jupiters because, weirdly enough, these planets are found very close to their stars, not like our Jupiter, which is found relatively far out in our solar system. And I'll talk a little bit about why these are quite weird and how they've really challenged our understanding of planet formation, but we'll get there in a minute. Right, so we're going to start off with, what is a planet? It sounds like a bit of a funny question, but even the International Astronomical Union, who are the big body in charge of making particular decisions like delineating the constellations in the sky and things like that, it's a body, a professional body made up of professional astronomers. Even they had to refine the definition of planets in 2006, so pretty recently. And so to show you what the IAU, or International Astronomical Union definition is that the object, at least for our solar system, must orbit the sun. If it was a different system, it must orbit a star. It must be massive enough that it is roughly spherical in shape. It's pulled into that shape by its own gravity. And it must also have cleared out the neighborhood of its orbit from other debris. So it mustn't be in a dense environment like the asteroid belt, for example. It must have a relatively clear orbit. And of course, this was a very controversial decision made by the International Astronomical Union, because what it meant was that Pluto, which had until then been our 9th planet in the solar system, got demoted to minor planetary status. It made quite a lot of people unhappy, including the leaders of the New Horizons space probe that had already set off to look at Pluto. Yeah, they couldn't do that. But it's still a very interesting object. Now we know, here it is out here, Pluto. It's actually just one of many small bodies out past Neptune's orbit in what we call the Kuiper belt. And it's a very dense, actually, region out in the outer reaches of the solar system, and there are many such bodies orbiting the sun at that distance, and this is why Pluto is not classified as a planet on its own, because it hasn't got a clear orbit. And in fact, it's not even the largest body at that distance. There are other bodies larger than it. And it was very serendipitous that it was ever found at all. It was completely found by mistake, actually. Now, looking at our own solar system, this is a bit of a funny image. Now, it's hard to depict the solar system because there's a whole lot of different scales involved. In this picture, you'll notice straight away that there's something wrong. Why is Jupiter the same size as the Earth? Okay, that's a problem. It's really just to try to fit everything on the page. And so what's also quite difficult is that what people forget, because most of our images of the solar system where we try to fit all the 8 planets and the sun in, is that the gaps between the planets as you move further and further from the sun get larger and larger as well. So it's actually really difficult to depict the solar system in a nice way in a picture. So I'm just giving you those 2 caveats to keep in mind when you look at this. But the important thing that I would like you to take away is that in the inner reaches of the solar system, we have our rocky planets. Mercury, Venus, Earth with our moon and Mars. Then we have the asteroid belt, and then we have out in the outer regions of the solar system our gas giant planets. So these are the ones that you would have trouble standing on. You wouldn't be able to. Whereas these are the nice rocky bodies that you would be able to stand on. And when you look at their compositions, they're rather different. And so one of the things that planetary scientists have to answer is, how on earth do you form a solar system like this, where you've got a sun at the center, and you've got rather differentiated planets? You've got rocky ones made out of heavy materials in the inner reaches, and at the outer regions, you've got these gas giants. Another thing that you have to explain, if you'd like to understand how the solar system formed, is that all the planets, if you were to look at our solar system edge-on, all their orbits lie very close to a plane, except for Mercury, which is a little bit off. And all the orbits are elliptical, as was discovered by Kepler. And just to remind you, because I'm going to be using the terminology of orbits a bit today, this is what an elliptical orbit looks like in a very simple drawing. So here we have the sun at one focus, and ellipse has a second focus as well. Here is a planet in orbit, and if you take the line that joins the two longest, that goes across the longest part of the ellipse, that's called the major axis. This is called the minor axis. And the part that I'll talk about quite a lot is the semi-major axis of the orbit. It's half the major axis. And the reason that I do that is because our orbits in the solar system and in many systems are quite close to circular. In other words, a circle is just a special case of an ellipse where the two foci are on top of each other. And in that case, the semi-major axis is just the radius of the circle. Okay, so when I talk about the semi-major axis of an orbit, I'm talking about the radius of the orbit. Okay, so those I'll probably interchange a bit. So something I neglected to tell you yesterday when we spoke about star formation is that at the same time as stars form, so do their planets. So as the cloud of gas collapses, you saw that when we looked at that simulation, you saw the small blobs coming out and that they were spinning. And around those spinning blobs would have been clouds of the same material, which as the blobs contracted and got ever smaller due to angular momentum, the material around them would have contracted to form a disk around them. And the planets form out of these disks, these protoplanetary disks. And so the planets form out of exactly the same material as the star. Okay, so I'll explain how that works now. And I'm not telling you nonsense. Here we have some real images of protoplanetary disks. So this is a whole collage of Hubble Space Telescope images of protoplanetary disks in the Orion Nebula. And what's happening here is that the young protostars, the forming stars in the center of these disks, are releasing radiation, which is heating up the dust, yes, that word again, in the disk, and that dust is re-radiating in the infrared part of the spectrum. And so it's actually relatively easy to find stars at this stage of their evolution, or should I say planets at this stage of their evolution. Once they become individual planets, it becomes much more difficult. But at this point, because the dust is evenly spread out over a very large area, it's actually easier to find them. So this is why there's so many beautiful examples of these early planetary systems. So these are in the process of forming planets. Now, to explain and answer to the question yesterday, what is this dust? I went and checked up on myself again, and it's the remains of what is ejected from supernovae. So carbon is very common in this dust in the form of graphite. You find iron crystals, you find silicates, but the main thing to sort of take away is that it's the heavier elements which can actually form small particles, not just in single atoms, but that clump together to form crystals or molecules. So we find silicates, iron, carbon, for example, in the form of graphite. And we know about the interstellar dust because when we do observations of starlight, what happens is that these dust grains actually, in interstellar gas clouds, tend to polarize the light that passes through them. And so that gives us an idea that actually a lot of these dust grains are elongated. They're quite long, made up of many individual atoms. They're about 10 to the minus 7 meters across. They're very small. And this is the sort of shape. But we don't know very much about these dust grains. They're still, there's a lot we don't understand still about them. But that's basically what I can tell you for now. Now, if we go back to the solar nebula, or the protoplanetary disk, the way that we think that you could form planets that are rocky close to the star and planets that are gaseous far from the star all actually depends on temperature, because this disk of material is made out of the same stuff. It doesn't matter whether you're close or far away. But this is a little cartoon almost of probably what happened in our solar system. So this is distance from the forming sun, and this is temperature in kelvins. And these are the positions of Earth, Jupiter, and Saturn today. Now, close to the sun, where Earth is today, it would have been very hot in this protoplanetary disk. And so at those high temperatures, over 1,000 Kelvin, you would only have been able to condense out into solid form heavy elements like iron and silicates, magnesium, etc. Further away from the protostar, however, the temperature drops. And so the further away you go, the cooler it gets. And so not only can heavy elements condense out into solid form and larger molecules, but so can lighter elements and molecules. So water ice and ammonia ice, for example, can condense out of the cloud as well. Closer to the protostar, these lighter molecules would not have survived. They would have had to be in gaseous form. And so this is how we understand that the inner planets formed differently, formed into a different form than the outer planets. The inner solar system, you could only condense out the heavier elements into solid form, and in the outer solar system, only the lighter ones as well as the heavy ones. And so in the outer solar system, you could grow a planet out of both the rocky material and the ammonia and the water and all the lighter things. And you could start to grow gas giant planets. Closer in, you could only grow rocky planets. So although the solar nebula consisted of the same material, depending on where you were in it, you could only form where that material could condense out. There is less heavy material than, heavy elements. There are less heavy elements in terms of abundance than light elements. And so this is also why the rocky planets are smaller. There just isn't as much heavy stuff as the light stuff. And so you wouldn't be able to grow a rocky planet the size of Jupiter because there wasn't enough material. Now, there was only a certain amount of time. So what would have happened is you would have condensed out these little solid grains as they're orbiting the protostar in the disk. They would have started to clump together. They would have grown larger and larger. As they grow larger and larger, they get a larger gravity. It becomes easier for more stuff to stick to them. They could grab onto a bit of gas because they could hold on with their gravity to lighter things as things cool down. And so by the time, after about 1 million years, these gas giant planetoids would have been able to grow quite large and hold on to quite a lot of the lighter gases. The inner planets, planetoids, would not have been able to do that yet. And then at that stage, the sun would have gone through, and as part of its formation phase, a very active stage where it would have had very active solar winds. And the solar winds would have been winds of charged particles that would have streamed away from the surface of the protostar and would have literally blown off the gas of the solar nebula, or the protoplanetary disk. That's why when we look out today, we don't see reams of dust and gas between us and our neighbor planets. That gas has all been dissipated now. And so the large planets would have had to have formed before this happened. It's also why the lighter planets weren't able to hold on to hydrogen and helium. Any hydrogen and helium that they would have possibly been able to gain would have been blown off at that stage. So that's in a nutshell how we think our solar system formed and why the inner planets and the outer planets are so different in appearance. So now I'm going to zoom to exoplanets. And as I said earlier, the first exoplanet, 51 Pegasi, was found only in 1995 around a main sequence star. There was actually an earlier exoplanet that was discovered around a pulsar, of all things, but it was a bit of an anomaly, and people at the time were not looking for an exoplanet. It was sort of discovered serendipitously. And after that, there was a large, many years before we found the first one that we were actually looking for. Now, as of today, we have, as humanity, have found 3,565 exoplanets. And it's quite amazing to think that back in 1995, we'd found one. That's a huge leap. There are many different methods that we've used to find them, and I'm going to go through them in this lecture. Out of those 3,500 odd, 602 of these are multiple planet systems. So these are systems more like our solar system, where it's not just one planet revolving around a star, but actually a number of planets in a system revolving around a star. And I was just plotting by the year, because I've taught the first year astronomy course for a number of years, and every year I go and check on the database over here. This is a very, very nice website for the general public and scientists alike, where they list every exoplanet that has been found, all the candidate ones, all the confirmed ones, and all their vital statistics, like their radius, their mass, everything that's known about them, including a link to the scientific paper in which they were published. So it's a really great resource. And over the years, I go and look every year to see how many have been found. And I just made a quick graph last night, actually, to see how it's grown over time. And it really has made an amazing leaps. So the blue bars are just showing the number of confirmed planets. And the orangey red bars are showing you how many multiple planet systems have been found. So with every growing year, more and more are being confirmed. I like this artist's impression of a subset of the confirmed exoplanets. So what this person has done is they've drawn the Jupiter-like gas giant planets that we've discovered, sort of similar to Jupiter, given them different colors, and then you can see in between them a lot of the smaller planets that have been discovered. Now, these are obviously just an artist's impression. We can't, with our current telescopes, image many of these planets at all, let alone get sort of surface features like this. But it's great. At this point, it's in our imagination, but with the upcoming 30-meter telescopes and even larger ones, the aim is to be able to measure directly or observe directly what these planets look like. So that's exciting times ahead for planetary science. Now, the reason that they're so hard to detect is because planets only shine because they are reflecting the light from their stars. So they don't have their own radiation that they emit, and so that means they can be very faint. And these are two examples of planets that are actually being directly imaged. So this is 2M1207. I like its name, and it's about 5 times the mass of Jupiter. It's lying quite far from its star, 55 astronomical units, and it's imaged using the Very Large Telescope. And this one over here is GQ Lupi. That's the name of the star, and then the name of an exoplanet is always the name of the star with a letter next to it. And so that's the planet over there. And as you can see, it's very hard to do this. If the planet is not far away enough from its star, its light will be completely overwhelmed by its star. And so when you image stars looking for exoplanets, you will be looking preferentially for planets that are actually quite far away and also quite large, because they must have enough surface area to at least reflect, but they must be far away enough not to be overwhelmed by their star's light. This is a really nice image of a planetary system with 4 planets. 1, 2, 3, 4, and this is the central star. And the reason that the central star looks odd is that they've actually masked out, they've tried to mask out the star's light so that you can find the exoplanets more easily. Now, imaging is not a good way to go after them, as I think I've convinced you. In fact, out of our 3,500 odd planets that have been discovered around other stars, only 76 of them have been found through imaging. So a very small group. Most of our exoplanets have been found through the following two methods: radial velocity measurements and transit measurements. This is the overwhelming majority over here. And I'm going to talk about how we use this method, the transit method, gravitational microlensing, which is quite an interesting one as well, in the following. Now, when you have a stellar system with a planet in orbit around a star, you can imagine it like this, right? So you have, although it looks as though the planet is orbiting the star, what's actually happening is that they are both orbiting what we would call a common center of mass. If the star is very massive and the planet is very small and relatively close by, the center of mass will be probably inside the star, but not in the very center of the star. It will be offset a bit. And depending on the system, the center of mass will be more or less offset. But be that as it may, what will happen is that as you observe the star in this system, it will appear to jiggle at you because it's actually moving around its center of mass. And so it will appear as though it's not staying stationary, but that it's jiggling back and forth or side to side. And here I'd like to show a little animation of how this works. So here it's very small, and I did this on purpose because I want you to keep an eye on the star, not the planet. So the planet, as the planet is moving around the star is also moving around its common center of mass, and at certain times it'll be moving towards us, and at certain times it'll be moving away from us. And so it'll appear to be jiggling in the sky. This is a bigger version. Oh, sorry, let me go back and just do the bigger one, where you can see it much more easily. So this is a very nice one. So if you were to see this face on, you'd see the star moving up and down. If you were to see the system edge on, you'd see the star moving back and forth. And so this is the key to how we do these detections. We don't look for the planet. The planet is way too faint. What we do is we look for the jiggle of the star. And how we would do that, here's the clue: redshift and blue shift. We're going to observe the spectrum of a star. So this is just a star spectrum. Here we have absorption lines. Now everyone's very familiar with this. By the end, you'll be going, please, not another spectrum. And so here's some hydrogen lines in the spectrum of a star. And this is just the other way to look at it, with intensity and wavelength on the x-axis. And what you would do is you would observe a star, and you would observe it over a number of intervals. So you observe it tonight, and then you take a spectrum tomorrow, and then you take a spectrum the next day, and the next day, and the next day. And you would notice, if it has a planet around it, that the spectral lines will be shifting from the rest position as that star moves towards you or away from you. And as we discussed on Monday, that movement in the apparent change in wavelength of the radiation is because of the Doppler shift. And the Doppler formula will allow you to get back the velocity of that star with respect to you. So you look for the change in the wavelength from its true wavelength divided by its true wavelength that you know from the laboratory, and you can get out the velocity of the star, and whether it's moving towards you with a blue shift or away from you with a red shift. And then what you will do is you will plot the velocity for each of those times. And if you're lucky, and the star does have a planet around it, you will see a pattern like this. So this is the actual, what we would call the radial velocity curve, for 51 Pegasi, the first planet observed around a main sequence star. So this is the time in days. So they actually would have had to have taken a spectrum more often than once a night. They would have actually observed the star many times during a night, because this is only over 4.2 days. And they would have measured the radial velocity of the star at each of those times and made a plot. And here you can see this is when the star is moving away from us. Here it's not moving, here it's moving towards us, here it's moving away from us again. And so you see this regular motion towards and away, and that's telling us that that star has a planet around it, because there's nothing else that would be causing that jiggle. It's a very nice repeating pattern, and so from this pattern you can actually get the period. You can see over here that when the pattern repeats, that's one period. That's how long it takes the planet to go around that star. So it's a very, very powerful method of detecting exoplanets and measuring the time of their orbit around their stars. The most used method, I suppose I should say, for finding exoplanets is called the transit method. So I'll come back to radial velocity just now. But this is the second method that has been used to discover more than 2,000 exoplanets. If we're lucky enough to observe a system where the plane of the orbit is in our line of sight, then what we might observe is the planet passing in front of its star with respect to Earth. And if that happens, when the planet moves in front of its star, it will block out a small amount of the light from that star as it moves across in front of it, sort of like an eclipse. You could call it an eclipse. And then when it moves out from being in front of the star, you will get back to the full starlight. So this is what this picture is showing you. So here we have the star. Here the planet is starting to move in front of it. So the light from that star is starting to dip. As the planet moves in front of the star, it's blocking out a certain amount of light. And then when it starts to move again from being in front to away from it, it will gradually increase again, and then the star will be back to its full strength. And this is a method that has been used, as I said, to detect more than 2,700 planets. This is a nice illustration where we actually have an animation of how it works. So this is the light, and this is time that you would measure of the star. So again, you're not seeing the planet itself, you're just seeing the star. The planet is much too small to actually resolve, but as it moves in front of its star, the light coming from its star will appear to make a dip. And then you know something passed in front that would have to have blocked out some of the starlight. So we could just watch it again, it's quite nice. Now, obviously, the only problem with this method is that you can only notice it if you are at the right angle with respect to the system. If the system isn't edge on, then you won't observe the eclipses. So this is a nice triple planet system, so you'll see the dip from the first planet moving in front, and now the second planet's going to cause a dip, and the third planet overlaps, so you get a deeper dip, and then it comes up in a funny way like that. So looking at these patterns of light curves, we call this kind of graph a light curve, where we plot light against time for a star. And looking at these patterns, astronomers can try to disentangle how many objects would be in orbit around that star and what's causing these different dips. And so this is how you would be able to figure out that there were actually 3 planets around that star, not just 1. Now, of course, if you use this method, the important thing is that what if something randomly just happened to pass between us and that star, and block out some light, and it was just a chance alignment? That's a reality that can happen. And so when you use this method to detect planets, you need to detect a repeated dip in the light, so that you know that at least it's real and that it will repeat at regular intervals. Okay? Otherwise, it could have just been something that happened to move in front between us and that star and has no relation to the system at all. So you can't just measure one dip and say, woohoo, I found a planet. To confirm it, you have to go and follow up and make sure you measure 2. And of course, that has implications for how long you have to observe a star for. If a planet has a very big semi-major axis and takes a very long time, more than 100 years, to go around the star, we won't have seen those kind of systems using transit measurements. Okay, so using transit measurements, we've only seen relatively short period or smaller orbit planets around their stars. Now, the telescope that's been responsible for most of the transit measurements is the Kepler telescope. It's in space, and it's not in orbit around the Earth, but actually in orbit around the Sun. It lags in our own Earth orbit behind us, so it follows Earth as we go around the Sun. Kepler trails us. And it was put in space to originally have a 4-year mission, and the aim was to observe more than 100,000 stars. And the aim was really to try to, one of the main aims of looking for exoplanets is to try to find habitable planets, try to find out if we're alone. That's what's so fascinating, not just dead balls of rock, but actually whether, there's life on some of these other planets. And so the aim of Kepler was to try to look for stars that were similar to the Sun. So I'm getting my "oh, be a fine girl, kiss me" in out of order, so it was F, G, K stars, so that we would possibly find systems that were similar to our own solar system. And Kepler's been incredibly successful over its mission. It has found more than 4,500 candidate planets, and of those, 2,300 odd have been actually confirmed. It's made amazing discoveries of very strange systems, and I'll give you a few tastes of those to come. It's even found a planet around a binary star. So in that system, you've got 2 stars orbiting each other, and around them, you've got a planet orbiting them. So you would, if you lived on that planet, you'd look up and you'd see 2 stars in the sky. So people call that the Tatooine planet. For anyone who's a Star Wars fanatic, it would have been the world that Luke Skywalker lived on as a kid. It's also, in Feb 2013, it actually found such a tiny planet that it was only slightly larger than the Moon. And this is because Kepler has a very, very precise photometer. In other words, its camera can measure incredibly small changes in the luminosities of the stars it measures. Very tiny dips, because a moon-sized planet passing in front of a distant star would make such a tiny dip in its light. But Kepler is sensitive to that. It's able to do it. It was designed to do that. So this is just some of the vital statistics as of 2015 about Kepler. Unfortunately, a couple of years ago now, some of the steering hardware on board the telescope stopped working, and so they can't aim it exactly how they would like to anymore and re-observe stars in the same way that they were doing before, but they're still using it, and it did fulfill its main first mission criteria, so it was a successful mission, and it's actually going on for longer than anyone really expected it to. I quite like this picture that NASA put out of some of its planet candidates. So this is just another artist's impression. The little disk over here is the size of the Sun, as viewed at the distance. If we put our Sun at the distance of the stars that Kepler is observing, and you can't see the Jupiter, but it's on my screen a tiny black dot. And this is some of the stars around which Kepler has found planets. And these little black dots are the apparent sizes that those planets would look like if you could see them. And so it's looked at quite a large range of different stars and found many different, a huge variety of planetary systems, actually. I like this one too. This is just an animation that somebody put together after the first wave of Kepler planet discoveries, looking at some of the different multiple planet systems and making a little orrery out of them. It's very fun to watch. In fact, NASA took it to a whole new level where they actually put out a bunch of travel posters. So they you know, like a 1930s travel agency, they got these wonderful posters made up of, you know, encouraging people to visit other worlds. So I really like these. This is Kepler 186f, and for the people at the back who can't see it, it says, where the grass is always redder on the other side. And the thing about this planet is it's orbiting a star that's much redder than our sun. And of course, our plants are green because our sun's light peaks in the green part of the visible spectrum. And so if you want to maximize the energy to make your food, you're going to have green leaves. And that's, if you want to maximize the energy that you want to make food and you're a plant on this planet, you're probably going to have red leaves. So that's where the joke comes from. This is Kepler 16b, affectionately known as Tatooine. This is where your shadow always has company. You've got two suns. Absolutely, I love these posters. And then this one is quite interesting. This is a planet that was discovered which hasn't got a star. So this was not actually discovered by Kepler. I'm now trying to rack my brain and remember how it was discovered. But it was a planet that was discovered floating off in space on its own. Nice if you want where the nightlife never ends. So, you know, disco planet or something. And probably what happened to this poor planet was it would have had to have formed with its star, but at some point, if its star had a rather intense gravitational interaction with some other body or another star, it could have got caught up in these interactions and slingshot off into interstellar space, where, shame, it's all alone now. But anyway, quite cool. So the third method that I'm going to talk about quickly is a rather interesting method of looking for exoplanets. And this method is called gravitational microlensing. And this is quite a cool effect that happens. So basically, if we're the observer over here in our telescope and we are looking at a distant star, bright source, what can happen is if an object moves in front of a distant source, it bends space around it because it's got mass. And so now we're thinking in a sort of general relativistic way. It bends the space-time, it distorts it. And so what can happen is that the light coming from this distant star is lensed by the foreground object. And this background star can actually appear brighter for a short period of time. So as something massive moves in front of it, the background object looks brighter. And sometimes if the thing, and it happens that if the foreground object is a star that has a planet orbiting it, then you will be able to pick up the planet signal that way. Now the thing with this method is it's a bit of a strange method. Planets have been found using it, but you can never go back and repeat this particular measurement because it's a chance alignment. From the Earth, that we have a distant object and a completely unrelated star that happens to move in front of that one and also happens to have a planet, and we happen to see that event take place. That event is never going to repeat itself. And so you would have to follow up that system using other means. You'd have to try and find the object, maybe using radial velocity or some other method. So this just highlights how it works. So here's your background star that you're actually looking at. And here is the foreground dimmer, fainter object. It's a star which has a planet around it. And as it moves in front of this distant star, what will happen is that the light from the background star will brighten because it gets lensed. And if you have a planet around you, then you'll get a little blip on that lensing signal to indicate that actually there was probably a planet that caused yet another little distortion of space there. So I'm going to show you an animation. So there's your background star, and this is the fabric of space-time. And here is the foreground object moving. Here's the observer on Earth, and you can see they're trying to illustrate the light waves being distorted from this background object as the foreground object moves in front. So obviously, because these are chance events, you have to do surveys of the sky repeatedly of the same background objects over and over and over again, and quite often, to monitor whether they change in brightness with time, and whether you'll be able to actually map out that change in the brightness and see any planetary blips. So that's why that method hasn't recovered nearly as many exoplanets as say, the transit or the radial velocity, which are much more focused searches. So quickly, I'll go into very, very briefly and not in a lot of detail how we then extract the properties of exoplanets, because I've spoken a little bit about how they're hot Jupiters or how they are rocky planets, or some of them we call super Earths. And how on earth do we know this when we just measured the light from the star? I'm just going to highlight again, I think it's so cool that you can find a planet by just looking at the star. So this is the radial velocity plot that I showed you earlier. And as I mentioned earlier, the period of this wave pattern, you can fit that, and you can extract then the period of the orbit of the planet around its star, how long it takes that planet to orbit its star once. You can also get the orbital period by using the transit method, of course, because you can look for how long it takes before you get the next dip in the star's light. So every next dip, the time that it takes between those is how long it took the star to go around the planet to go around the star once. Now, if I want to extract the size of the orbit, or the semi-major axis, here I've just simplified it, and we're moving from an ellipse just to a circle here. So this is the radius, or the semi-major axis. We can use Kepler's laws. Good old Kepler. So if this is the period that you've just measured, either from your transit or from your radial velocity, you can use Kepler's laws. This is just, these are just numbers. This is the gravitational constant of Newton. And over here on the bottom of the fraction is the mass of your star and the mass of your planet. And here is your semi-major axis. Now, in this case, the mass of the star you can actually estimate. And we discussed how you could do that yesterday. If you've got a main sequence star, and you know its spectral type, and you know its luminosity, you can put it on the HR diagram. And because you know that the mass varies from the top to the bottom of the HR diagram, you can estimate the mass of the star that way. Compared to the star, typically the mass of the planet is very small, so we can neglect it in this case, and we can extract the semi-major axis that way. Now, how do we get a handle on the planet's mass? Well, using the Doppler method, we can measure, we can get an idea of the force exerted by the planet by the star on the planet due to gravity, and knowing the mass of the star, the semi-major axis, Newton's gravitational constant, then we can go and extract the mass of the planet. Now, obviously, if we're using the velocities, the recession velocities of the star, everything's fine and well if we're looking exactly in the plane of the orbit, so that all the velocity of the star is in the direction coming towards us, and all of it's in the direction moving away from us. But if we have our orbit at a slight angle, like this, but towards us like this, then the component of the velocity towards us will not be the true velocity. It'll be just a portion of it. And so the inclination of the orbit is quite important. You have to try to get a handle on that somehow to be able to get out the true mass of the planet. So it's always regulated by the inclination of the orbit. So obviously, if you have an exoplanet system that you are interested in and you're trying to learn more about, then you try to observe it in as many ways as you can to try to weed out all the things you don't know about it. In terms of how big they are, how we measure their radii, well, transit is a very nice way to do this. So if you know the radius of your star, which we spoke about yesterday, if we know the luminosity of our star and we know the surface temperature of our star, we can calculate its radius, if we know how far away it is. And then you can calculate the dip in the light caused by the planet when it moves in front. And from that, you can find the ratio of their two radii. And then if you know the radius of that star, you can easily calculate what the radius of your planet is. So that's how we know how big these things are. And then, of course, if you've got the mass and you've got the radius, then you can find out the density of the planet, because the density is just proportional to the radius cubed. And then you can understand whether the planet is probably a gas giant with low density or a rocky planet like Earth, which will have a higher density. So these are how we tease out those parts of the puzzle from the observations. Now, the last thing I'd like to show you is the thing that we have to always keep in mind when we do any kind of physics or astronomy, and this is selection effects. So this picture over here, unfortunately, I'm not sure if you can read very clearly at the back. This is the semi-major axis, and this is the mass of the exoplanets. And all the dots on here are exoplanets that have been confirmed. And in fact, you can go and make this plot yourself if you have some time and you feel like messing around on that lovely database that I mentioned at the very start of the lecture. You can go and choose by kind of method and different masses, and you can plot lots of things against each other. It's actually great fun, and learn more about exoplanets. Now, this is using all the methods that we have detected planets with. And you can see that if you were to just look at this is large semi-major axis over here. This is short. It looks like at large semi-major axes, the planets are all massive. It looks as though you don't get any low-mass planets with big semi-major axes. That would be weird, right? I mean, why would that happen? So you've got to think a little bit. And you've got to think about how the measurements were done, because this is the key. If we look at only the radial velocity measurements, that's that portion of the plot. So now what I've done is I've gone and I've said, okay, I'm going to extract out of here all the planets that were found using radial velocity. And here they are. They aren't any over here, and they're missing over here. And this is showing us what is called the bias of the method. So what's happening with the radial velocity is that you're finding quite massive planets, which are relatively far from their star, because you're wanting to get a big wobble in your star. You're wanting to be able to see the wobble of your star. A very small planet's going to cause a very small wobble. A very low mass planet. A more massive planet's going to cause a bigger wobble, so they're easier to measure. And so that's the bias in your method. If we look at transits, that, in other words, exoplanets discovered using the transit method, they lie in this part of the diagram. They all lie at small semi-major axis. They're distributed over quite a wide range of mass, but they sort of stop here. Why? Now, if you had only looked for exoplanets using that method, and you didn't know anything about that, you'd think that all planets must live out to only this semi-major axis, and that there weren't any at higher semi-major axes, at higher distances from their stars. But again, this is just because of how we've done this. We have to remember that the Kepler mission was 4 years long. And so the longest period of an exoplanet going around Kepler is 4 years. We haven't measured for long enough to find ones that take longer than that. And according to Kepler's laws, if you take longer to go around, you're at a further distance. And so we just limited by how long we've been observing using this method. And then lastly, imaging. That really shows you a nice bias. If we were only looking for planets using imaging, we'd miss all these low mass and small semi-major axis planets, and we'd only see these ones that are far from the star and very massive. And that's because those are the ones that are easier to spot using that technique. And so when we draw conclusions from our scientific data, this is always something in astronomy and physics that you have to be very, very careful about. You have to remember, how did I do the measurements? And not only what have I seen, but what am I missing? Because what am I missing is a very important question to ask when you're trying to understand the conclusions. So when you look at the plot altogether, this is another way of looking at the data. So this is now orbital period instead of semi-major axis, and this is the planet radius. All the yellow blobs here are the Kepler transit planets. And the other very interesting thing is that using Kepler, the overwhelming majority of planets that we have found using Kepler are actually Earths, planets that are between 1.4 and 4 times the mass of the Earth. And this is really interesting. I mean, if we think that what they've done is they've taken the Kepler data, now we know that it has biases in it. They've tried to unbias it. They've tried to understand what could we be missing, and they make the following plot. So over here is planet size, where Earth is 1, down here. And this is the average number of planets per star. So they've tried to extrapolate, given what Kepler has seen, given what we've seen with other measurements, trying to understand the biases and undo them. On average, per star, you see about 1/3 of a planet of this mass. And per star, you would see 0.05 of a planet of 4 Earth masses. Okay, so it sounds a bit funny, but what you're saying in effect is that every 3rd star has a planet around it that has the mass of Earth. And I think that's quite amazing. Before 1995, we hadn't seen any stars with planets around them. Now, every 3rd planet probably has an Earth-sized planet around it, every 3rd star. In fact, it would be hard to find a star that doesn't have a planet around it. Really hard. In fact, it's quite funny because when people are doing radial velocity measurements now to find planets, you want to be able to compare, when you're using your spectrographs to understand the systematics and the offsets, you want to be able to compare to a star that doesn't have a planet so that you can check it's not wobbling and that the wobble you measure is a real wobble. But now it's really hard to know because what if that star that you're using as a standard star has a planet and is wobbling? So it's actually quite funny that it's getting trickier and trickier to do these things these days. So if you did the extrapolation that there are about 100 billion FG case-type stars in the galaxy, then about 30 billion Earth-like planets should exist in our galaxy. And that really starts to make you think about, wow, are we alone? Now, the thing that I want to quickly get back to on this picture, and which we started the lecture with, were these so-called hot Jupiters. Now, if I go back to that picture I showed you before, this is the semi-major axis over here again, and this is the planetary mass. This green line over here is the distance of the Earth from the Sun. And this area over here are objects which are Jupiter mass or larger. And now when you look at it, you think, she told me how the solar system formed. Big gassy planets can't form that close to the star because it's too hot there. What was she talking about? Was she making it up? We don't think so, but these planets caused a real headache for people who were thinking about planet formation and all the models that model our own solar system. You know, it was a big thing. Why are we finding all these hot Jupiters with the radial velocity method? What we think is actually happening is that these planets don't form out at the distance at the distance that we observe them today. What we think has probably happened to these planets is that they did form further out in their protoplanetary disks where the material was cooler, and then as they were spinning, they could have lost some angular momentum to the other material in the disk, and they could have moved in closer to their stars. And so we think that's probably what happened. And the warning is really, you know, when you've got an example of one, a sample of one, our own solar system, you know, you can't, it doesn't always tell you the full story. The other interesting things on this plot are the fact that actually there are many planets that are actually closer to their stars than even Mercury is to our Sun. In other words, less than 1/3 of the distance between the Earth and the Sun, and that are small and rocky. And why doesn't our solar system have planets like that? And it's thought that actually maybe we did originally have small rocky planets closer to the Sun than Mercury, but over time, if their orbits were disturbed, they may have actually spiraled into the Sun, and we don't see them anymore. So we'll never know for sure, but it is possible that our solar system once had them. Now, obviously, what you would like to do once you've found all these 30 billion Earth, potential Earth analogs, is you want to try and find out where these stars live with respect to their sun. Because if you want to look for extraterrestrial life, then you need, if you're looking for life similar to that we find on Earth, you need water to be able to survive in liquid form. And so what you need is for your planet to live in what is called the habitable zone of your star. Depending on the mass of your star and its luminosity, obviously, your habitable zone will be at a slightly different distance. So for very small, faint dwarf, red dwarf stars, then the habitable zone will be closer to them, and for brighter stars, they'll be further away. And for our own solar system, the habitable zone is between Venus and Mars's orbits. And so if we just look at our own solar system and we look at the planets that are in the habitable zone, only one of them does support life, at least at the current time that we know of. Venus is far too hot and dry. It has no water on it anyway. And Mars is currently too cold. And although perhaps it had life in the past, we wait to find out. Kepler has found quite a few potential life-supporting planets. These are planets that are found in the habitable zone of their stars. So there's quite a few candidates, and obviously these are the subjects of intense follow-up. Scientists will be going after these stars, trying to do spectroscopy of their atmospheres, trying to look for organic signatures. And so I'm just going to leave you here with, are we alone? And lastly, you can be a planet hunter yourself if you would like to. So this is a great website here called planethunters.org, where the Kepler Space Telescope has put all their data up for citizen science. And it's actually great fun. So what you do is you look at the light curves, transit light curves for stars, and we look through them and see whether we can find transits that the automatic computer algorithms missed. And the algorithms had missed a few. And so they keep them up there for people to look through and classify. They also obviously find a lot of variable stars and all sorts of things in this database. And so if you're interested, it's really fun, and it's very hard to pull out once you get stuck in the classifying. So yeah, set an alarm or something. And I think I'll end there. Thanks very much. Right, we've got time for a few questions. Yes?
How far away is the nearest of the candidate planets?
Golly gosh, you've got me now. I'll have to look it up for you. Oh, actually, no. Alpha Centauri has a planet around it, and Alpha Centauri is 4 light years away, 4.5. So our nearest exoplanet is actually as close as our closest star, apart from the sun. And so that's very exciting. It was only recently found at the end of last year, and so there's lots of people following that up.
And that's about 4 light years?
4.5-ish, yeah. So that's very close. That almost feels like you can contact them if they're there. Bit of a slow email conversation, but still. Any other questions? Yes?
What is the nature of the solar wind that blew away the gas?
It's one of the stages that the early sun goes through. I'm not 100% sure what gives rise to that precise process and what's going on at that time. But I can ask my stellar colleagues what gives rise to that very intense wind at that point. It's called the T Tauri phase of the star's life, because the first star that was found to exhibit these kinds of solar winds was found in Taurus. But I don't know exactly the processes. I'm not a stellar astrophysicist. Sorry about that. Yes?
One thing that's always puzzled me is, if you look, is the sky sort of, as we look at astronomers look at it, do they divide in sections? I'm just worried that they're all looking at the same place.
Oh. You know, that's actually a very good point. There are certain parts of the sky that are much better studied than other parts. And that's really just because telescope time is so expensive. So if you want to do very deep observations, they're going to take you a long time. If you want to look at very faint objects or very distant objects, You have to always, how it works in astronomy is there are telescopes in the world. Some of them are available for anybody to use. Some of them are only available if your institution is a member of that particular telescope, for example. But it's always a competitive process. So as an astronomer, you have to write a proposal explaining to the time allocation committee why your science is the coolest thing since sliced bread and why they various methods. And what I mean by this is that these are gas giant planets, similar to if you imagine what Jupiter looks like. We know what it looks like. We've got many images of Jupiter from various spacecrafts, from telescopes. And these are called hot Jupiters because, weirdly enough, these planets are found very close to their stars. Not like our Jupiter, which is found relatively far out in our solar system. And I'll talk a little bit about why these are quite weird and how they've really challenged our understanding of planet formation. But we'll get there in a minute. Right, so we're going to start off with, what is a planet? It sounds like a bit of a funny question. But even the International Astronomical Union, who are the big body in charge of making particular decisions like delineating the constellations in the sky and things like that, it's a body, a professional body made up of professional astronomers. Even they had to refine the definition of planets in 2006, so pretty recently. And so to show you what the IAU, or International Astronomical Union, definition is that the object, at least for our solar system, must orbit the sun. If it was a different system, it must orbit a star. It must be massive enough that it is roughly spherical in shape. It's pulled into that shape by its own gravity. And it must also have cleared out the neighborhood of its orbit from other debris. So it mustn't be in a dense environment like the asteroid belt, for example. It must have a relatively clear orbit. And of course, this was a very controversial decision made by the International Astronomical Union, because what it meant was that Pluto, which had until then been our 9th planet in the solar system, got demoted to minor planetary status. It made quite a lot of people unhappy, including the leaders of the New Horizons space probe that had already set off to look at Pluto. Yeah, they couldn't do that. But it's still a very interesting object. Now we know, here it is out here, Pluto. It's actually just one of many small bodies out past Neptune's orbit in what we call the Kuiper belt. And it's a very dense, actually, region out in the outer reaches of the solar system, and there are many such bodies orbiting the sun at that distance, and this is why Pluto is not classified ones that you would have trouble standing on. You wouldn't be able to. Whereas these are the nice rocky bodies that you would be able to stand on. And when you look at their compositions, they're rather different. And so one of the things that planetary scientists have to answer is, how on earth do you form a solar system like this, where you've got a sun at the center, and you've got rather differentiated planets. You've got rocky ones made out of heavy materials in the inner reaches, and at the outer regions, you've got these gas giants. Another thing that you have to explain, if you'd like to understand how the solar system formed, is that all the planets, if you were to look at our solar system edge-on, all their orbits lie very close to a plane, except for Mercury, which is a little bit off. And all the orbits are elliptical, as was discovered by Kepler. And just to remind you, because I'm going to be using the terminology of orbits a bit today, this is what an elliptical orbit looks like in a very simple drawing. So here we have the sun at one focus, and ellipse has a second focus as well. Here is a planet in orbit, and if you take the line that joins the two longest that goes across the longest part of the, that is a planet on its own, because it hasn't got a clear orbit. And in fact, it's not even the largest body at that distance. There are other bodies larger than it. And it was very serendipitous that it was ever found at all. It was completely found by mistake, actually. Now, looking at our own solar system, this is a bit of a funny image. Now, it's hard to depict the solar system because there's a whole lot of different scales involved. In this picture, you'll notice straight away that there's something wrong. Why is Jupiter the same size as the Earth? Okay, that's a problem. It's really just to try to fit everything on the page. And so what's also quite difficult is that what people forget, because most of our images of the solar system where we try to fit all the 8 planets and the sun in, is that the gaps between the planets as you move further and further from the sun get larger and larger as well. So it's actually really difficult to depict the solar system in a nice way in a picture. So I'm just giving you those 2 caveats to keep in mind when you look at this. But the important thing that I would like you to take away is that in the inner reaches of the solar system, we have our rocky planets, Mercury, Venus, Earth with our moon and Mars. Then we have the asteroid belt, and then we have out in the outer regions of the solar system, our gas giant planets. So these are the... All right, good evening everybody. I think it's 5:30, so we can start. Today's lecture will be on extrasolar planets, which are also sometimes called exoplanets for short. And these are planets which orbit stars other than our sun. And I'd just like to preface the lecture with, I am by no means an expert on exoplanets, but I've had great fun preparing this lecture because it's such a fast-moving field. It really, the first exoplanet that we discovered around a main sequence star, and now everybody knows what a main sequence star is, was only in 1995. So this is an incredibly new field of astronomy, and it's literally, it feels as though we're discovering a new planet a day, pretty much. And so it's incredibly exciting, it's fast moving, and there's a huge amount of work still to be done out there, especially with the new upcoming large telescopes that are being built. This picture over here is an artist's impression of some of the so-called hot Jupiter planets which have been discovered.